Hi, in this video I'm going to talk about second order non-homogeneous differential equations. So a non-homogeneous differential equation is basically when you don't have equals zero, you've got equals something else on the right hand side. That's all you need to know about this, okay? But there are second order differential equations. I've got another video on this, an introduction one. If you've not seen that, please watch that one because this one follows on from that, okay? So in this one, you've got equals f of x and there's a method to it, which I'll take you through. The first step is you solve it as if it was a equation equals zero. So just ignore that, just solve it equals zero, and then you go through the normal rules, and that gives you part of your solution. And then what you've got to do is find what the final solution is by trying a particular, what we call particular integral. Now this first part of the solution when you solve it is called the complementary function, and then you need to find a particular integral. These are the rules, okay? So the idea is that on the right hand side you could get equals a constant, okay? You could get equals a linear term, you could get equals a quadratic, exponential, or a cosine or sine. Nothing else in this syllabus. So I'm covering A-level mathematics, further mathematics. These are the only ones that have come up in this particular syllabus. So what I'm going to do is I'm going to take you through an example of each one. And here are the differential equations. So notice they're all the same on the left hand side, okay? It's just the right hand side is different, covering each of those cases when you've got either a constant, a linear term, quadratic, a exponential, or this one is a sine. Okay, I'll go through each one of these separate examples. Now, because the left hand side is the same, the first bit, finding the complementary function, is identical. So I only need to cover that once. Okay, so I'm going to do that now. So this one, for the complementary function, what you need to do is, first of all, solve when this differential equation is equal to zero. So for this, you need what's called an auxiliary equation. So the auxiliary equation is going to be m squared minus 5m plus 6 equals 0. Solve that quadratic, usual rules, and you get here the case where you've got two distinct real roots. So as a reminder, this is the scenario for two distinct roots, alpha, beta. It's going to be a e to the alpha x plus b e to the beta x. So the part that we're looking for here is y equals a e to 3x and then b e to the 2x, and usually that will be our general solution. It is for when it's equal to 0, but when it's equal to something else, that's only part of it. So this part of the general solution is what we call the complementary function, and these are terms that you need to be aware of. You need to know the term complementary function, or CF for short. Now we've found that, we need to find what's called the particular integral. That is what we need to add on to that to get to our final general solution. And for this, I'm just going to show you that table once again. So when you've got a constant term, what you're going to do is you're going to try y equals lambda, and you'll see why that's going to work in a few minutes. Okay. And now when that is done, you have y equals lambda, you've got to substitute it back into the original equation. So you can clearly substitute y into that. You have to differentiate, find dy dx to substitute something in there, and then find d to y dx squared and substitute into that. Okay. So I'm going to do that in the next set of working. So y equals this, dy dx, clearly 0 because lambda is a constant, and also d to y dx squared is also 0. And when you substitute these into there, you're going to get 0, subtract 5 times 0, plus 6 times lambda equals 3. So clearly 6 lambda equals 3, lambda equals a half. And then that is it. That is what our particular integral will be. Y is equal to a half. Then you put them together, your general solution will look like this. The beginning bit, the complementary function, CF, y equals a e to 3x plus b e to the 2x, and then added to 1/2. And this is our general solution. Why does that work? Because we've tried a particular value for y, and when we've substituted in, we found a value for lambda for which it works. We found a value for lambda for which this equation satisfies, it's equal to 3. And because it works, that must be part of the solution. Okay? So trying something and then substituting it in, it kind of gives you your answer and it helps to explain why that works as well, because it satisfies the equation. So that's the first example. So the second one is when you've got this is equal to a linear term. Now when it's a linear term, you've got to try a linear value for y. Not just lambda x, but a linear term could have some constant value as well. So for any linear expression, you try y equals lambda x plus mu. And then same again. So your standard approach is solve this equals 0, gives you what's called a complementary function. Try a particular integral, depending on what that is. find dy dx from that, d2y dx squared, substitute it into here, and work out the values of these letters, lambda, mu. That's it. That's your general method for every one of these types of questions. I'm just going to work it through with you. So differentiate this, you're going to get lambda, and then differentiate again, you're going to get 0, substitute it into here, you're going to get this here, expand the brackets, you're going to get this, and solving this one, what you're going to do is you're going to equate the x terms, so 6 lambda x must be equal to 2, so 6 lambda equals 2, giving you lambda must be equal to 1/3, and then this here must be equal to 0 because there's no constant term on the right hand side. It's as if you've got plus 0 there. So when you've got lambda, you can work out what mu is because that has got to be equal to 0. So mu is equal to 5/18. And then that gives us our particular integral. So our solution must be the complementary function added to the particular integral 1/3 x plus 5/18. That's it. And that's our general solution. Okay. Next one. This is when you've got a quadratic on the right hand side. So assume you've gone through all of this. Okay, you've got the complementary function. You then need to try a particular integral. This time we're going to try something that's of quadratic form. So lambda x squared plus mu x plus nu. And then we just find dy dx, d2y dx squared, substitute into this and get the values of lambda, mu and nu. Okay, that's it. So here we go. So this is what we're going to try. So dy dx is that. You can check these and go along. d2y dx squared is that. Substitute this into here. And then you've got this here. So d2y dx squared, -5 times that, plus 6 times by that, gives you this. Expand the brackets. Get all the x terms together, the x squared terms together, and the constants together. And similar approach to before, you're going to say that the x squared terms must be the same. So 6 lambda equals 3. So lambda then must be 1/2. These terms, well, there's no x squared, so there's no x term, so that must be 0. So 6 mu minus 10 lambda equals 0. So using lambda as a half, you can work out mu's, turn it to 5/6. And then this is also 0 because there's no constant term on the right hand side. So substitute this in here to work out nu, and that turns out to be 19/36. And that gives us our particular integral. So our general solution must be this, the complementary function plus the particular integral bit, which is lambda x squared, mu x, and then nu. And that's it. That's our general solution for that one. Okay. Next case scenario, you've got an exponential instead. So here you've got to try y equals lambda e to the x. I hope you can see why this works. You've got to try something of that form so that when you substitute in and differentiate again, you're going to get like pairings on the left and right hand side that can match up and that you can solve. And that's why the whole thing works. If you can find a value of lambda such that this works, then that's it. That must be the solution. So here we go. This one, I always find exponentials nice and simple to differentiate because it's going to be exactly the same. dy dx, d2y dx squared is just equal to that. Substitute into the original differential equation, you're going to get this. And then the thing I like about these ones is you've got e to the x in each of these terms, you can just divide that by e to the x. So lambda, -5 lambda, 6 lambda, 1. And then that makes it quick and simple to solve. The value of lambda must be 1/2. And then that gives us the particular integral. So the final solution, the general solution, is this here on the end, with the complementary function here, of course. Whoops, there we go. And then one final one. So here we go. So with this one, you don't always get sine and cosine together. Usually it's just either sine or cosine. You can get both, but rarely both. If you do get both, the angle will be the same. Notice here, you've got the angle marked omega there. It will be the same. So if there was a cosine term, it would be something cosine 3x. Okay. Now, despite the fact it's only sine, you've got to try both of these as your particular integral. It's no good just trying that. It's no good just trying lambda times sine 3x. You think why? I didn't give you much thinking time, but when you differentiate this, you're going to get something in terms of cosine. So when you substitute it back in here, you're going to get a cosine term, at least in here. And you need to have something on the right hand side to match that up. You need sine on the left and right, cosine on the left and right as well. So for the particular integral reading you've got just sine x, you've got to try sine x and cosine x. And similar for when you've got just cosine x, basically you've got to try them both. So either that, or both of them, you've got to try this as your particular integral. That's just something you need to remember. If you get it wrong, by the way, it won't work. You won't find a solution. Okay? So easy scenario to think about is you try a particular integral, doesn't work, assume you've not made any mistakes and they're working, it's not the right particular integral to try. You've got to try something else. Okay? So here we go. So y equals this. You've got to differentiate that. You can check it with me if you wish. So differentiate this, you get this. Second derivative, you're going to get this. And then you need to substitute back into the original differential equation. So you'll have d to y dx squared, subtract 5 times dy dx plus 6 times y equals 13 sine 3x. The next screen shows that. So it's a bit of a squeeze, but I've managed to fit it all in. Sorry, the writing's a bit smaller. So I'll just step back so you can see it all in one go. There we go. So here, and then if I just rewrite it, so the method is put all the sine terms together. So sine, there it is. And the cosine terms together, there it is. And then what you can do is you can match this sine 3x term with this sine 3x term. So the bracket there must be equal to 13, which is the next bit there. And of course that simplifies a little bit because that and that is just going to be this. And then this one here, that must be 0 because you've got no cosine 3x term there, so that it must be equal to 0. And that will simplify again because you've got mu there, so that simplifies to this line. These simultaneous equations, how you solve it's up to you. Maybe you times that one by 5, subtract that one. Maybe you divide the bottom one by 3, make mu the subject, put it back in there. Either way, it's not too difficult to solve. You get your value of lambda and mu, and that gives you your particular integral. So your general solution will be the complementary function, which is this here, and then a particular integral. So negative 1/6 sine 3x is 5/6 cosine 3x. And that's it. And that's your general solution. Right, I'm hoping that helped you. I hope you made a lot of sense about that. Of course, you can always rewatch, rewind, pause if you want just to pick things up again. Okay. Thank you very much for watching, and I'll see you again. Bye-bye.